This is the halting problem, set of those strings which correspond to a Turing machine and input, and then this particular Turing machine should halt on that input with an output bit. Okay. So, basically recursive problems with an instance is given to you. Now, can you design a Turing machine? That is the question, right? So, it captures the question, is there a Turing machine to test whether M alpha halts on X? Right. So, this is the question which we are formalizing here by defining the language halt, because the yes strings are the ones where M alpha halts on X. So, if you want to recognize this language, decide this language, then you have to design an algorithm to test whether M alpha is actually going to halt on X. And the problem is that when you are given a bad input where M alpha does not halt on X, what will you do, because it is an infinite loop. So, it is, in other words, you want to test for infinite loops, and that is that looks hard, and in fact, we will prove that it is completely intractable. There cannot be a solution. So, its uncomputability was shown by Church, which was a very tedious proof, nearly a century back, and then much simplified by Turing. So, Alan Turing, when he defined this Turing machine, which we now call Turing machine, the problem, the proof of halting problem being uncomputable became very simple, as you will see now. So, halt is not computable. Proof. So, suppose it is decidable by a Turing machine M0. Okay, so the proof will go by contradiction. Suppose it is computable, and then there is a Turing machine M0 which is deciding halt, which means after finitely many steps it can tell you whether M alpha halts on X or not. Say it outputs 1 on alpha comma X, if M alpha on X halts. 0 if M alpha X does not halt. Does not halt means it goes in an infinite loop. Okay. So what can we do with this information? So, actually impressive thing in the proof is once you know that once you have assumed in this case that M0 exists, you can actually feed M0 to M0. Okay, that will give you the proof, and that will actually first give you a contradiction, and that will show that M0 cannot exist. So what happens when we feed M0 to M0? So let's do that formally. So define Turing machine M prime as follows. So given input alpha, if M0 on alpha comma alpha is 1, then output 1. Okay, so what is the behavior of M prime? So M prime takes input a string, which you should think of as a description of a Turing machine, and you feed alpha on the input alpha, alpha and alpha to M0 as input. So basically M0 will simulate the Turing machine described by alpha on alpha itself, right. So here we are actually sending, we are trying to say so let's go back to the definition of M0. So M0 is a Turing machine is an algorithm that decides halt, right. So when will M0 alpha alpha be 1? Only when, in fact, if and only if M alpha halts on alpha. Sorry, it should be the opposite. That is the beauty of it. Doesn't halt. If M0 doesn't halt, if M alpha doesn't halt on alpha, then M prime will negate the answer. Okay, it will output 1. What if M alpha halts on alpha? So in that case, simulate M alpha on alpha computation and output the negation of what you get. Okay, so this completes the definition of M prime. What M prime is doing is, it is exploiting M0 to check whether M alpha is going to halt on alpha or not, on itself or not. If it doesn't, then it outputs 1. If it does, then it negates the answer. That's M prime. So what is the contradiction? Well, we still don't have a contradiction, but we have a Turing machine. We have defined M prime, which is doing something funny. And contradiction will come when you run, as I had suggested, M prime on itself. That is where the contradiction will happen. So let beta now be the encoding of M prime, Turing machine M prime. That is, M prime is M beta. And ask the question, what will M beta do on itself? That's the question which will lead to a big insight. Okay, what does this Turing machine beta do on itself? So beta on beta. So if M beta on beta, now remember that there is no problem in M prime halting, it always halts, right, no matter what input alpha is, it always halts. So maybe I should write that. there is no issue about M prime not halting on some inputs. It always will halt because it either outputs, it halts and either outputs 0 or 1. There is no infinite loop issue in M prime. So, M beta beta can have only two possibilities, either it halts gives you 1 and it halts gives you 0. That is the only possibility. So, what does it mean when it halts and give you 1? So, then it means that either M0 on beta beta is 0, but I mean basically it is saying that either M beta on beta does not halt, which will obviously contradict that M beta beta is 1. So, this is actually coming from step 1, right. Think of this as step 1 case. That is one place where you can get output 1, but that happens only when M0 beta beta is 0, which is which gives a contradiction. Can't halt. So, that leads to a contradiction, right, because we are in the case where M beta beta value is 1. So, obviously it halted. So, it cannot be that you got output 1 in step 1. Let us go to step 2. So, or M beta beta halts, but in step 2 getting an answer 1 output 1 means that the value of M beta beta has to be 0. So, which again is a contradiction because we are in the case where M beta beta is 1, right. So, hence M beta beta cannot be 1. That is what we have deduced. So, now let us go to the other case. So, this means that M beta beta has to be 0. That is the only case left. In this case, output 0 in these two steps, when do you get output 0? It is only possible in step 2. And which means that M beta beta should be 1. Which is also a contradiction because we have deduced that M beta beta is 0, right. So, you have to maybe look at this proof many times before you completely understand what just happened. So, what happened is we assumed that M0 exists, halting problem solution exists. From that we designed this M prime which kind of negates the answer and also takes care of the infinite loop. So, that M prime is, it always halts. And then we are asking what happens when M prime is given M prime itself, right. And there we have ruled out all the cases, which means that M prime cannot exist, which means that M0 cannot exist. Right. So, proof by contradiction. So, this means that M prime can't exist, which means that M0 can't exist. right. So, we had assumed that M0 exists. So, we have now deduced that halt is uncomputable. Right. So, this is a first breakthrough in insight, that once you have formalized machines, then machines cannot understand machines, right. At least machines cannot, even machines cannot even decide whether other machines will stop, right. That is an uncomputable question in that model of machines. And since we believe that Turing machines are the only possible machines, so halt just cannot be computed ever by any model. So, this proof technique is called diagonalization argument. Why is that? What is the diagonal here? Okay, so to see that, draw this picture. So, list your Turing machines M alpha here. The rows basically are indexed by Turing machines, and the columns are indexed by input x. Okay, so both obviously rows and columns are indexed by strings, and now you ask for this row string, you fill the answers on the column string being used as input. And what this Turing machine M prime is doing, it is negating the answer, right. So, it is actually working here. It is negating the answer of what? M alpha, alpha on alpha, right. So, alpha comma alpha is referring to the first diagonal entry. You can think like that. Then for the second string is the second diagonal entry, alpha on alpha. Then third is the third alpha acting on the third alpha input as input, and so on. Okay, so this is the diagonal being talked about. So, this is the diagonal. So, the machine M0 that we define, or M prime that we define using M0, it is actually only looking at the diagonal, these values, and negating it. So, once you negate the diagonal, then you get so that is what then leads you to contradiction, because now when if this M beta existed, I mean when M beta you act on, you simulate M beta on beta, that will give you a contradiction. Okay, so it was all about these diagonal entries. If you have negated all of them, then that gives you the contradiction. There cannot be a Turing machine in the row indices, right? Because row indices, if any index that you look at, it will be unable to give you the right answer. So, beta cannot come here, for example. m beta cannot exist here, right? Because when you see its answer here, you will see that it's negated. Okay, so this is the diagonalization technique. It is actually not the first time that Turing used it. I mean, definitely in computation, it was the first time, but in math, in other places, this idea had appeared. So let me just write that a Turing machine is designed that disagrees with m alpha alpha for all alpha, right? So that Turing machine m beta cannot exist. That was the contradiction. So this technique we will see in this course as well, which is why I have given you this recap. And before this, it was used in other math results. So this technique was used in earlier foundational So what were those foundational results? So first is, and I think this is the very first where this technique was invented by Cantor. So Cantor's proof of the uncountability of reals. Uncountability of reals. Okay, in 1891. So what is this result? This says that the set of reals, they are in bijection with subsets of natural numbers. I mean, this you already know. You can write any real as basically like looking like a subset of natural numbers. You can just think about the reals between 0 to 1. So they are in decimal representation. You can think of the binary string appearing after the decimal point, and that is a subset of, that defines a subset of natural numbers by their positions of 1. And what Cantor showed is the following, that this is strictly bigger than the set of natural numbers. There is no bijection. Okay, so there cannot be a bijection between natural numbers and the set of natural numbers, the set of sets of natural numbers, or set of subsets of natural numbers. So reals is strictly bigger than natural numbers. In fact, you can also put rationals here, and because rationals are in bijection with natural numbers. Okay, so reals are strictly bigger than rationals, though obviously both are infinite sets. So Cantor was the first one who actually can compare two infinities, okay, by his argument. So maybe try to prove this by the diagonalization trick as a homework exercise. Second is Russell's paradox. Slightly later. So Russell's paradox says that certain sets don't exist. Okay, so you, for example, you cannot say define let S be a set that contains everything. Okay, so such definitions he showed, they don't make sense. And the way he showed it is by showing that the set Y which contains x's such that x is not contained in X. This doesn't exist. Okay, so this also you can do, so you can prove it using the diagonalization trick as an exercise. So although I have written the definition here, but this definition actually doesn't make sense, which is the paradox. Third is probably the most famous one, Gödel's incompleteness theorem. Which came much later, around the same time as Turing actually. So incompleteness theorem says that there are actually statements in math which you cannot prove or disprove. It's just impossible. So there exist unprovable statements. Okay, so unprovable means that you can write down, or Gödel wrote down a statement which you cannot prove it's true, you cannot prove it's false. Okay, the true or false cannot be decided. So their truth is undecidable. Okay, and this ties actually very well with also halting problem. Yeah, so some of the really big big steps in math, also philosophically speaking, they actually involved the diagonalization argument. Okay, so enough of this. So now we move on to more complexity things. Only looking at problems that are computable. So for that, let me define the notion of reduction. How to compare problems that are computable. Let's say in an equal way. So a function f can be shown uncomputable okay, we are still in this possibly uncomputability regime. So okay, how can you show other functions to be uncomputable or other problems to be uncomputable? That you can do by, if you can, you will get that if you can reduce halting problem to your problem, right? So that because once you have a reduction, obviously your problem cannot be easy, because if it was easy, then you will also solve halting problem. So your problem is also hard. That's the idea of reduction. So a function can be shown uncomputable by reducing it to so notice the direction, by reducing halt to f. Okay, that's the correct direction. That would mean that f is also uncomputable. It's very hard. So that is design a computable function f prime such that for all inputs halt on x is the same as. So, what will f prime do? F prime will basically modify the input x and then apply f. Okay, so reduction is nothing but a composition, okay, by where a computable function is involved, that you have to design. So, this f prime is the key thing. This you have to design. This is called the reduction. So, which will basically, when you actually wanted to solve halt on x, so instead you modify x and give it to f, and that will solve halt. Okay. So, this third function, this is called reduction. If this exists, then it shows that your problem is harder. And we write this as halt reduces to f, Turing reduces. Okay, there is a Turing reduction. And this means that f is also uncomputable. So, we will make it more precise for complexity in the next class.